Welcome back. For today's calculus problem, we're going to be looking at a curve where we're going to be using local linear approximation to find some y value at some given x value. So the curve they give us is x cubed plus x tangent y equals 27, and it passes through a point 3 comma 0. And they want us to use local linear approximation to estimate the value of y at x equals 3.1. So whenever you have a problem that's using local linear approximation, they just want you to use a linear equation, so in the form y is equal to mx plus b, and m is really the same thing as dy dx. So dy dx is just some slope at some given x value. So the slope that we're looking for is going to be, should be at 3.1 or very close to it. So fortunately, they give us an ordered pair 3 comma 0, which is, and these x values are very, very similar. So we can use this ordered pair in this original equation here, and then we can solve for our dy dx by plugging that in. So, but before we do so, we need to get a dy dx out of this equation. So we start off with this equation, x cubed plus x tangent of y is equal to 27. So there's no dy dx yet, so we need to take the derivative of this. So we take the derivative with respect to x. And when we do that, we get 3x squared plus, and again, we'll take the first derivative of x is 1. Hold the second, so we get tangent of y. We're just doing product rule on x tangent y. Plus hold the first, and then take the second. So the derivative tangent y with respect, and taking the derivative with respect to y is secant squared y, but we're taking the derivative with respect to x, so we need to add the chain rule dy dx. And then that's going to be equal to 0 because the derivative of a constant, any constant value is just 0. So at this point, we could get dy dx by itself, but it's actually easier to just plug in the values for 3 comma 0. So x is equal to 3, y is equal to 0. So let's just take this ordered pair, plug it into the equation, and then that'll make the algebra a little bit easier when we solve for our dy dx value at 3 comma 0. So we get 3 times 9, because 3 squared is 9, plus tangent of 0 plus 3. And instead of writing secant y, I'm going to write 1 over cosine of 0 quantity squared. And this is times dy dx, which is what we're solving for, and that's still equal to 0. Tangent of 0, that of course is just equal to 0, and then 3 times 9 is 27. So we get 27 plus 3 over cosine 0 squared. Cosine of 0 is just 1. 1 squared is just 1, so this is just 3 dy dx, and that's equal to 0. So we subtract the 27 over to the other side, so we get, and divide by 3, so we get a dy dx is equal to negative 9. And this is really your slope value that we're going to use here in our linear approximation. So now we can get our linear equation set up in the form y is equal to negative 9x plus b. So we still need the y-intercept. So to find that, we just use the ordered pair 3 comma 0, because that is the point on this curve that we solved the dy dx for again for that curve. So we plug it in, we get y is equal to 0, and then this is equal to negative 9 times 3, and again because we're using this ordered pair right here, plus b. So then when we solve for b is just equal to 27. And that makes sense because if we were to look at, so let's go ahead and just plot this out really quickly. If we were to look at what was given, we're given that we have some ordered pair 3 comma 0 here. So 1, 2, 3. So this is 3. And we know that the slope is negative 9. It's pretty steep. So we're going to go all the way. Let's go all the way like this. It's pretty steep. And this has a slope, or dy dx, but actually I'll just call it a slope. So this slope is equal to negative 9, and the y-intercept here is 27, which we just calculated, which makes sense. Pretty high up, but that makes sense based on based on this really steep negative slope. So what we're solving for is we are solving for the y value where x is equal to 3.1. So right next to it here, this is where x is equal to 3.1. And this is not going to be the exact value of this curve, but it should be very close. And we have no idea what the curve looks like. It could be doing, let me change the color. It could be doing, let's say it looked like this, for example. We don't know what it's doing. And let's say this was actually the y value on the curve. But this line right here will give us a value that's very, very close to the actual y value on the curve. So changing our color back here, this right here, for this 3.1, that would be on this point right here, which would give us this value right here, which is y as a function of 3.1. So that's the value that we're looking for, which is very, very close. As you can see, there's not even hardly any space here between this line for the linear approximation and the actual curve of the function. And again, this is not a function, this is a curve, because it probably violates the vertical line rule, which I did not check. But anyway, let's just go ahead and finish the problem out. So we have y is equal to negative 9x plus 27. And then now we're going to say y is a function of 3.1, because we're trying to approximate the y value at x equal to 3.1. This is equal to negative 9 times 3.1 plus 27. And then 9 times 3.1, well, that's just negative 27.9 plus 27. And then that's equal to negative 0.9.